Hi, in this video we are going to be discussing the tutorial 4 and better understand the introduction to OS concepts and a very important thing on the states, okay, of a task and the transitions. Okay, so um, again this tutorial is important because this is the first tutorial that we are introducing you to the OS environment. Okay, so it's important you have a good foundation, okay, and understand what is really happening at the very basic level. Okay, and with this you also have the background knowledge that you need, okay, for the lab exercise that you will be doing as well. Okay, so the first overview is the state transition diagram. Okay, so this is an important diagram because this shows us the different states that a task can be in once it is entered into the system. Okay, so the very first step is of course to create a new task, and that is to call OS thread new. Okay, so when we call OS thread new and we create a new task, it is automatically admitted to the ready state. Okay, because by default, when you first create a task, it already has everything you need, so it goes into the ready state. Okay, there can be many number of tasks in the ready state. Okay, so you can have up to n number of tasks in the ready state, but only one, okay, will be selected, okay, to run. Okay, and that uh, decision is made by the OS scheduler. Okay, so this scheduler, okay, is basically what we term as a high level manager that looks at all the tasks, okay, the end tasks that are currently in the system that are ready, and we transition one of them to the running state. Okay, and how do you make this decision? For an RTOS based system, what is important is the decision has to be made based on priority. Okay, so that is what gives the RTOS that real-time capability. Okay, because a task that is created to be of higher priority means it is important, so when it is ready, the scheduler should allocate that task to make use of CPU time to execute its code. Okay, so that is a important aspect of priority, of using priority to schedule tasks. Okay, of course there can be a lot of different type of scheduling policies which you will see in the lecture on scheduling. Okay, but the RTX RTOS, okay, which is the RTOS system, uses priority as a means to decide who will transition to the run state. Okay, so when I'm in the running state, two things generally can happen. One is I can have a timeout. Okay, so this timeout and going back to a ready state, that is basically what we call a yield. Okay, a yield is basically a function you can call OS yield, basically in our OS. And when you call that, basically what you're doing is you are voluntarily giving up the CPU and going to the ready state. Okay, so when you are in the ready state, it's important to note that you have all the resources you need to actually make use of the CPU. Okay, you have everything, but it's just that the scheduler has not chosen you to run yet. Okay, so that is why you are in the ready state waiting for your chance to run. Okay, now another thing that can happen is you can go to this block state. Okay, when you go to a block state, it means that you are running. Okay, you are running, that means you're making use of the CPU, but along the way you wanted some resource, okay, and you were not able to acquire that resource. Okay, and because of that, okay, you wanted something and you couldn't get it, so because of that the OS has transitioned you to a block state. So your block means you are actually waiting for something. Okay, and when you're in a block state, you definitely cannot be making use of the CPU. So what will happen is, at some point of time when the resource that you wanted becomes available, you may get allocated to that resource, and when you get allocated to that resource, you will unblock and then transition over to the ready state. When you're in the ready state, again you have a queue. Okay, and of course the highest priority task in the ready queue will get to run first. Okay, so that is basically the overview of the different states in the system. Of course there is also another branch here, the release and exit. Okay, generally we do not consider these in embedded systems because embedded systems are designed in a way such that all the tasks will always be running, okay, and there'll always be some interaction between them, okay. This release and exit is generally for maybe a general purpose OS systems, like for example your Windows or Linux. Okay, you can open up a process, let's say your Internet Explorer or your Word document processor. Okay, and once you're done with it, you can close it. Okay, so you can exit from the process. And at that point of time, what happens is, of course, all the resources you are holding on to in terms of the memory or any USB or any bandwidth. So anything that you're holding on to at that point of time will be released. Okay, when you exit the task from the OS. Okay, but in our embedded systems concept, we do not usually have this situation. So once you create a task, it generally stays within the ready, running, or block state. Now, so we have this overview now. So let's go on to these questions. So the first question asking us is, task A is currently running. Okay, so task A is currently running, and it gives up the CPU voluntarily. Okay, so as I mentioned, when you say voluntarily means generally it is referring to a situation where you have all the resources. So you have all the resources, okay, that you want, okay, but yet you still want to give it up. So what will happen is you will go to a ready state over here. Okay, and once you go to the ready state, you will then wait for your turn, okay, based on the scheduler, and then you will go back to the running state. Okay, so task A will go to the ready state in this case. Okay, now next part B. Again, we have task A that is running, and task B becomes ready. Okay, so task B becomes ready. What will happen? So task B is a higher priority task, correct? And since our OS is based on a priority driven scheduler, okay, the moment a higher priority task becomes ready, it will automatically transition over to the run state, okay, by the scheduler. Okay, so the scheduler will do this, okay, and at the same time, since task A was running, if task A was running, that means it had all the resources it needed. But because somebody else more important, correct, a higher priority task came along, it is forced to give up the CPU. So in that case, it will transition to the ready state. Okay, so that is what will happen over here. Task A will go to the ready state while task B will go to the running state. Now task B is running. Okay, task B is running, and we know that task A is in the ready state. Okay, and at some point of time, task B requests for some resource and is unable to acquire it. Okay, so when you say you're unable to acquire it, means that means you cannot carry on proceeding, okay, without the resource that you want. So in that case, what will happen is you will or the OS will transition the task B to the block state. And since task B transition out to the block state, the CPU is free, so the scheduler will look at the queue again. Okay, and in this case, since task A is in the only other task in the queue, in the ready queue, it will transition to the running state. Okay, so that is what will happen over here. Task B goes to the block state, while task A goes to the running state. Okay, so now task A is over here, and task B is in the block state. Okay, so and after 5 milliseconds, the resource required by task B is available. Okay, so once the resource required, task B was waiting for some resource, and now that resource is available. Okay, so what will happen is task B will now transition from the block state to the ready state. Okay, and once it's in the ready state, again the scheduler will come in to see if task B is higher priority than task A, which is the case. And what will happen is then task B will transition to the running state, while task A will switch over to the ready state. Okay, so these are the sequence of things that will happen. Task B will go to ready because the resource is now available. And once it is in the ready queue, the scheduler will come in and he will see that, hey, task B is higher priority than task A. So I need to switch task B to running. Okay, and task A was running, so it will now go to the ready state. Okay, so again, whenever there is a task that is in the ready queue or tasks that are in the ready queue, the scheduler will always be there looking at the priority of these tasks and see who is the most important, the highest priority task, to switch that task over to the running state. Now in our RTX RTOS, this is basically what we will be doing in the first RTX RTOS lab. Okay, so in the lab manual, I'll be guiding you through step by step on how to create your own RTOS based project. Okay, and once you create it and you add this template code, okay, from the system, this is what you will see. Okay, and basically what you will see is after you adding all the RTOS components, of course you have new header files, okay, related to the OS. Okay, and in the main function, after the clock is updated, you have a OS kernel initialize function. This OS kernel initialize function is to make sure that all the requirements of the OS are fulfilled. Okay, so for OS to run, it may require certain hardware peripherals, generally like timer units. Okay, it will require a fair amount of memory. Okay, so all the resources that the OS needs in order to run will be sort of handled within this OS kernel initialize function. And once that function is created, okay, basically the OS is ready. Okay, and what we want to do is the OS kernel start. This function is basically the start of the OS. Okay, start of OS environment. Up till OS kernel start, everything else is still sequential. Okay, so when I come into the main function, when I start, it is still sequential. It is still line by line. Okay, but eventually once I hit OS kernel start, I will switch over to the OS environment. And as we saw just now, once you switch over to the OS environment, the main person who kicks in is the scheduler. Okay, who will look at the tasks that are in the ready queue. Okay, so generally what we like to do is we like to create a new task prior to starting the OS. So this task that we create will be the starting point of the OS once we switch over to the OS environment. Okay, so that is the done using the OS thread new function. Okay, so that is basically what you will see here. Now let's look at the questions related to this. So for the OS thread new function, when I call this OS thread new, you can see that I pass in three parameters. What are they? Okay, so these are the three parameters. Okay, so all of this detailed information is actually in the online documentation, which I've sent you all in the link in the announcement. Okay, so please refer to that for all the OS related functions. Okay, the documentation is very good. It's very clear. Okay, and they explain it very nicely. So, and they also give you a lot of sample code. Okay, so please go through those online documentation whenever you are unsure of what this OS kernel call does. Okay, and of course in the future when you talk about mutex and semaphore and all these other topics. Okay, if you're not sure how it works or exactly how to use it, go back to this online documentation. They have a lot of very good explanation and sample code for you to reference. Okay, for OS thread new, basically you can see that there are three parameters. For now, we are only focusing on the first parameter, and this first parameter is actually the name of the thread function. Okay, the name of the thread function. So this thread function is basically the main starting point for the thread that you're creating. Okay, as you can see, the app main thread is over here. Okay, and these two, okay, parameters. The first one is arguments. Okay, so just like how you have a normal function, you can pass in arguments. So when you create a new thread, you can also pass in some arguments. Okay, and the second one is attributes. Okay, so attributes are things associated with the thread, okay, and how we create it. One of the important things in attributes, which we will see later in subsequent classes, is priority. Okay, so as I mentioned, we're using a priority driven scheduler, which means the priority has a great impact on how the dynamics of the code actually will behave. Okay, so to alter the priority, we actually have an attributes field, okay, which we'll be exploring in the future labs. Okay, and another important thing if you look at app main is it is not a function call. So it is not the main calling app main or one thread calling another thread. No, there's no such thing as a thread calling another thread. All we can do is we can make the circumstances such that the thread can become ready. Okay, making sure that all the resources it wants are available. Subsequently, it is only the scheduler, okay, the scheduler who will decide who is going to run. Okay, so the scheduler is very important to decide who is going to be the task that is going to run next. Okay, so that is important. And another thing you will also see is all our threads are written in a infinite loop. Okay, so again, this is something very different from our normal multi-threaded single threaded programming. In our single threaded code, okay, when we write an infinite loop, we basically know we're going to be stuck there forever, correct? Okay, but in multi-threaded environments, all our threads are actually written as infinite loops. Okay, and of course, there has to be mechanisms in place to ensure that there is context switching and other tasks get a chance to run. Okay, which we will be exploring. Okay, now uh, let's look at this question. When will app main be called? Okay, so I think I just mentioned this. App main is never explicitly called. So when we call OS, when we create the thread, okay, with OS thread new, what we are doing is we are telling the OS environment that we are creating a new thread. Okay, and what is going to happen is once the OS starts, the scheduler will kick in and it will look at all the threads that are in the ready queue and select the one with the highest priority to start running. Okay, so OS kernel start function is basically the start of the multi-thread environment. Okay, and at that point of time, the scheduler will look at the ready queue and select the one with the highest priority to run. Okay, so that is the important thing here. It is not a typical function call. Okay, it is a kernel call that where the decision lies within the scheduler. Now, so the for loop, okay, in the app main, why is it there? Because in embedded systems, generally all tasks are written as infinite loops, okay, and then we will put in some mechanisms in place to ensure that other tasks also get a chance to run and all get a chance to use the CPU. Okay, so those are responsibilities of the developer, software developer. Now let's look at this code over here. So in this code, what are you seeing? Basically, in this OS thread new, we create admin, and basically once OS kernel start, you are switching to OS environment, so only threads will start to run. So the only thread in the system would be admin, and when admin runs, what will happen? I will call LED control, then OS delay, then LED control, then OS delay again. Okay, and the LED control basically switches on and off the red LED. Okay, now when we call OS delay, what happens? Okay, so OS delay is basically a blocking call. Okay, so you can refer back to the online documentation. Okay, so what happens is when the app main comes in, okay, initially you be in the ready state, correct? Okay, and then you will transition to the run state. Okay, when I'm in the run state, what will I do? I will call the LED on, okay, to switch on the LED, and after that I'll call OS delay. Okay, so when I call OS delay, what will happen? At this point of time, I'll go to a block state. So I'll be blocked, okay, for 1 second. Okay, after the 1 second is up, then what will happen is I'll come out to the ready state. Okay, then go to run state again, and then I'll do the LED off. Okay, and after I do LED off, then I again do the OS delay. So again, here to here is run, and after that, from here, the whole cycle repeats one more time. Okay, so basically OS delay is one of those kernel calls where you delay the task for 1 second, but in this 1 second, okay, this delay is a blocking call. That means I block my task. That means admin task will go into a block state. So why is this significant? Because in this 1 second, if this admin goes to a block state, that means I am freeing up the CPU. Correct, I'm freeing up the CPU, so other tasks that are currently in the ready queue can now be selected to go to the run state. Okay, so this is a very important and significant motivation for why we want to switch over to the multi-thread environment. Okay, because whenever the task has some downtime, okay, it doesn't need to continuously execute code, that time can be used for other tasks to execute their code. Okay, so that sort of environment allows us to fulfill a lot of things, okay, a lot of requirements within a very short period of time, okay, compared to our typical single threaded routine that we have been using all the while. Okay, so that is the significance of this OS delay. Okay, so in this explanation here, what it basically says is this 1000 refers to 1000 ticks. Okay, and in our current default setting, 1000 ticks is, sorry, one tick is 1 millisecond. Okay, so one tick is 1 millisecond, so 1000 ticks is 1 second. Okay, so as I mentioned just now, during that time what will happen is uh, the current thread will go to a block state. So if I go back here, you can see that during this 1 second, if this thread is blocked, what will happen is the whatever task that is in the ready queue will get a chance to run. But in our current system, there is no other task, correct? There is only admin. Now this is the only task that we have. So what will happen? What will happen is there will be other OS related tasks that will be executed in the background. So these are tasks that are run by the OS kernel, which are transparent to us. Okay, so things like timer threads, idle threads, and so on. These are threads that are hidden to us from the developer, but are actually running in the background. Okay, so as these threads run in the background, they are the ones that will actually be executing while there are no other user tasks, okay, in the system. Okay, and this question, if we use a normal delay routine, what will we see? If we had used a normal delay routine, okay, it would have been the same behavior, okay, in terms of observation. Okay, because if I replace this OS delay, okay, if I replace the OS delay with a normal delay, okay, 1 second, okay, that the kind of routine that we have been using in our lab so far, you would still see the same LED blinking effect. Okay, but the main difference is this would have fully utilized the CPU, okay, and prevented other tasks from running. Okay, so that is what is the drawback of the current approach, of the approach that we were using all the while, where we have a uh, explicit delay loop function, correct? Because the delay function that we have is actually nothing more than just a loop that runs for X number of times, correct? To sort of give us a specific amount of time delay. But now with OS delay, we know that we are putting ourselves in the block state, which frees up the CPU to do other things. Okay, so that is a big difference. Huh? Okay, so in this question, we are shown two threads. LED red thread and LED green thread. Okay, and both of them are created. Okay, so in the this is actually very similar to what you'll be seeing in your lab as well. Okay, so what you see is uh, when we call the OS thread new, okay, when we call OS thread new, we would have created the LED red first, and then the OS thread new would have created the LED green. Okay, so that is what you will see in your lab as well. And what is important is, since LED red thread was created first, it is the first to join the queue in the ready queue, correct? And since both of them are created with the same priority, okay, what will happen is you will see the LED red run, getting a chance to run first, followed by LED green. Okay, if I run this code, okay, what you would observe? Now, what did you observe? Okay, so let's look at the timing diagram over here. Okay, uh, okay, so this timeline diagram basically shows us very clearly what is happening. The LED red thread will transition from ready to run and will on the LED first. The moment I on the LED, I call OS delay. Okay, and this OS delay will block me for 1 second. Okay, and that point of time, what will happen is I will get a chance to transition to the LED green on function, which will switch on the green LED. Okay, and then delay for another 1 second. So you have to remember that this LED red on, okay, this whole code over here is very fast. Okay, that means for the whole duration of the 1 second that I am blocked, effectively majority of that 1 second, both red and green are on together. Okay, so what you would see is you will see it switch on as yellow color. Okay, red and green combined together. Okay, but if you step through the code, okay, in the lab, okay, when you try it, if you step through the code, you will see that the red actually is switched on first, followed by the green. Okay, but because it is that gap where the red is on before I context switch over to the green, that gap is very small. So you don't actually get to see it as red being on, you just see as both of them being on. Similarly, when I come out of the block, okay, I will off red first. So there will also be a short period of time where the red is off and green is on. Then only the green goes off. Okay, if you step through, you will see it. But again, it is very small, that time gap. So you see them both as on together and off together. Even though actually it is red on first, then green, and then red off first, and then green. Okay, so that is basically the sequence of operation. Okay, and of course in this week's lab, you're going to be exploring the some other explanation or better explanation for this behavior as well, because of the way the RTX RTOS actually deals with multiple threads that are of the same priority. Okay, so that is also quite interesting, which you will see in the lab. Okay, that is introducing you to this OS environment. Okay, but I think for this tutorial, I think it's important that you understand the whole idea of states, state transitions, and how the OS and its multi-threaded environment allows multiple tasks to be running concurrently. Okay, and fulfilling very complex requirements related to timing and deadlines. Okay, so that is the main objective of this tutorial. Okay, so in the lab you'll get to see a lot more and see it in action. Okay, so yep, all the best for the lab. Okay, so thank you.